In 2010, Chattanooga, Tennessee became the first U.S. city to offer high-speed broadband.
It's like having electricity 10 to 15 years before any other community has electricity.
Now it looks to do the same with quantum. The city has launched the United States' first commercialized quantum network.
China has some big loops of fiber. We've got some catching up to do, and Chattanooga is where we will do the catching up.
Interest in quantum technologies have exploded in recent years, billions of dollars pouring into the development of quantum sensing, quantum computing, and super secure quantum networks. Together, they have the power to change humanity, advancing drug discovery, space exploration, and enhancing new technologies like AI.
So if you think artificial intelligence is really cool now, wait till it's hypercharged with quantum.
Which is why
there is a quantum computing arms race.
It's a quantum nationalism that's come to rule the technology.
We want to push the limits of technology, understand if this is even possible.
This type of power in the hands of nefarious players could be a real danger.
Experts liken quantum computers to an atomic bomb for the digital age. A quantum network can prevent that. It provides an unbreakable link for quantum devices to send and share information.
And so a quantum layer, if you will, onto your existing infrastructure can provide that security. And that's a starting point for quantum networks.
Today, we dive into the emerging world of Quantum 2.0 and the race to rule it. Hear from Qubitekk, the company behind Chattanooga's quantum network, the latest test site of America's quantum ambitions. We'll also talk with researchers and analysts studying this growing field. So join me. It's time to get connected to the quantum arms race. Hi everyone, I'm Diana Blass. Welcome to another episode of Connected, the show that connects you to the latest buzz in tech. Today we explore quantum technologies, a topic that if you're not careful will give you a headache as you try to figure out its intricacies. But at the same time, you'll be amazed by its outcomes and potential, I promise you. You may be familiar with some of the current uses of quantum technology, like semiconductors, laser systems, and an MRI machine. Examples of devices that use what researchers describe as Quantum 1.0. Now, the race is on for Quantum 2.0. The next phase of a quantum revolution that includes quantum computers, quantum networks, and quantum sensors, an ecosystem that the city of Chattanooga, Tennessee hopes to bring to life with the debut of its commercial quantum network, said to be the first of its kind in the United States.
So there are a number of research networks that are really meant to kind of study some of the effects around quantum, but nothing like a commercial quantum network like they have in Chattanooga.
That's Dr. Duncan Earl, founder and CTO of Qubitekk, the company behind the quantum network in Chattanooga.
So at the end of the day, all a quantum network is a fiber optic network that is transmitting qubits, those are quantum bits, instead of traditional classical bits. And a quantum bit, without going into the physics too much, it's just like a single particle of light that you're trying to share between two nodes on the network. But that single particle of light carries a lot of information that's related to its quantum nature. And that's what we're trying to protect when we send these qubits between nodes. That requires a very special kind of fiber. It requires special receivers and transmitters, lots of special quantum equipment to enable that kind of a network.
The project began when the Department of Energy solicited Qubitekk to explore ways to better secure the electric grid, a critical piece of infrastructure that's become a prime target for cyber criminals. Qubitekk partnered with EPB, Chattanooga's power and telecommunications company, to develop the Quantum Protected Network, a cryptographic technique that uses quantum mechanics to provide unbreakable encryption. The solution enhanced grid security and secure communication between grid components. Looking ahead, quantum sensors can be deployed onto the network to precisely measure magnetic fields, temperature, and other elements to better monitor and control the grid. And quantum computers can eventually solve complex optimization problems. It's a glimpse into the possibilities that Chattanooga hopes to expand to other verticals outside of utilities with its quantum network.
So initial use cases would definitely be around security. So if you're a financial organization and you want to secure communications between your branches, this is a good application, although it's still fairly local. Until we have bigger networks there's going to be less applicability for secure communications. But that'll be where there will be a start. But then you can go beyond that. You can now bring in new sensors that you didn't have access to before. Distributed quantum sensors with greater sensitivity that can inform how you want to control your electrical grid or your city lights or whatever it might be that you're trying to optimize. And then eventually, and it's not too far out, but within the decade, you'll be able to tap into quantum computers that really can open up what you can do with automation technology and optimization technology.
Okay, so it requires an existing fiber network. That's the only kind of communication network it works with?
Well, right now, that's primarily the main means of building a quantum network. Although there are other efforts, like in China, to use free space, like satellite communications, to augment a fiber network.
Okay, well, I mean, satellite is definitely up and coming.
Yeah, right now it seems like it's much easier just to start with the fibers. And so that's why we specifically focused at Qubitekk on trying to identify where would be the ideal place to kind of roll out a fiber optic system where fiber was already well understood. Eventually we'd get to satellites too, but understanding what we could do with terrestrial fibers was the start. And that's what led us to EPB, that's the utility in Chattanooga, and the city of Chattanooga. They really have kind of the country's best fiber optic network, over 600 square miles of fiber optics that run all the way to the home. But most importantly, they own and manage that fiber. So when we wanted to put in a special network just for these quantum bits, just for these qubits, we could specify to them exactly what that fiber needed to do and where it needed to run, and they were able to help us do that.
EPB, Chattanooga's power and telecommunications company, is funding the quantum network at a cost of about $4.5 million and believes it'll recoup that investment within 5 years. In late July, the network became commercially available as a service. This means companies and researchers can connect their applications to the network, transferring data to multiple parties in a super fast and secure way. But Qubitekk expects there to be benefits to the city as well, as Chattanooga sets its sights on becoming a smart city. Already, it's home to the largest smart intersection in the United States, where you can find LiDAR deployed on the streets. The city will likely be one of the first to welcome autonomous cars and even V2X. This is a form of communication technology in which cars exchange data with their surroundings. And all that will require super fast processing powers, which Dr. Earl says quantum computers can do.
So if you want to make real-time decisions based on the data that's coming in, which you would for vehicle-to-vehicle communications and traffic control, you're going to need access to these newly emerging quantum computers. And that means you're going to need a quantum network. So it really becomes a critical piece of infrastructure for any city that's wanting to go smart or wanting to be tied in with all of these new technology developments.
So that was a lot of fun to learn about how quantum technologies can come to life in a city and the value it could bring. But outside of security, few benefits of a quantum network are readily available today, and experts debate when that will change. Let's turn to Professor Ido Wax with the University of Maryland and fellow of the Joint Quantum Institute. This is an institute that was created alongside the National Institute of Standards and Technology, underscoring the funds that the federal government is investing in this space.
Right now, I think there's already been a number of efforts, both here and in Europe and in China, to build large-scale networks that distribute quantum keys and to achieve very high levels of security. There's kind of another level of quantum networking that goes beyond just distributing quantum keys. We are seeing, we've seen in the past 5 years or so, the emergence of quantum computers that are starting to become quite powerful. And the ultimate goal from my perspective of what a quantum network would do is it would allow these quantum computers to communicate with each other. So, a quantum computer stores data in the form of qubits, not in the form of bits. And you can envision that maybe one day there'll be quantum data that needs to be stored and transmitted from different locations in order to do the kind of a distributed computation over many different sites. And that necessitates a way to get quantum information or qubits from one place to the other. And the current internet isn't really built for that. A lot of the steps in between that we use in the internet, they will destroy all the quantum properties. So you have to build a network based on elements that faithfully maintain or preserve the qubit, and its qubit coherence means that there's a phase information that the qubit uses, and it has to preserve that, and that requires a very different architecture than what we're used to. But you can leverage a lot of the things that we do have right now to build the network. For example, a lot of the fiber connections that we already have built, they could be repurposed for a quantum network. So it doesn't mean we have to kind of throw away everything and start from scratch, but it does mean that we have to develop new technology and kind of deploy it properly in the network so that it does things in a way that allow different quantum computers to move quantum data without losing everything.
Okay, and as we think about the security risks that quantum computers can pose, this idea that they can break encryption methods that many organizations use today, can the quantum network, specifically quantum key distribution that we're seeing in Chattanooga, prevent this from happening?
That's correct. That's correct. In principle, you can combine the concepts of quantum key distribution. So, for example, instead, right now, I think a lot of the quantum computers are just basically giving you remote login through the web. But suppose you wanted to really be careful about who has access to your quantum computer, and you wanted them, and you didn't want them to you wanted the wrong prevent wrong actors from accessing it. You can combine the principles of quantum computing with quantum key distribution to kind of ensure that you don't divulge some information. I think the more likely and interesting application is you kind of reverse it. Suppose I tell you I have a quantum computer. How do you know, right? You could give me right now. You would give me your data, and I would give you an output. And suppose I'm making it up. You're paying me a lot of money in order to do this, but I just have some regular computer that I'm doing it, and you don't have access to it. Well, with a quantum network, I can actually verify. You could know if I'm cheating. You could know if I'm just taking all of this data quantum data that you sent me, and just kind of trying a very big, complicated classical computer, or whether I really have a quantum computer that's doing the job. And so you could prevent me from defrauding you. And so that's another interesting application.
Well, lastly, what do you hope to learn from the Chattanooga test site underway? I mean, obviously, it was just unveiled, so we haven't seen many outcomes yet. But from a research perspective, it must be exciting to see this sort of solution unveiled.
Yeah, I think that what I hope to see is, first of all, just by trying to do this, and full disclosure, the technology to do everything we want to do doesn't exist yet. So we're still working on it, but it's progressing very fast. And so what I hope to see is a lot of different areas trying different things. And as these different things start to kind of evolve, and we start to learn about what works and what doesn't, we should hopefully have at least several different areas where we have quantum networks that are functioning well, that do interesting things. And then eventually, the hope is that they will all start to coalesce into a larger scale, big quantum network, similar to the way the internet evolved. And that's looking very far into the future. That isn't going to happen in the next 2 or 3 years. But overall, my hope is that by different people trying different versions of a quantum network and seeing what works and doesn't work, and simultaneously creating these kind of local and metro type quantum networks, we kind of lay out the infrastructure for what will eventually be a more kind of large scale quantum network, which is the kind that we like to have, where I can, in principle, transmit quantum data from Washington, D.C. all the way to the West Coast. We can't do that right now. We're very far away from that.
So that's interesting, right? The technology hasn't reached maturity, yet world economies continue to bet big on its expected outcomes. According to a McKinsey report, publicly announced investments into quantum technology companies in 2021 amounted to $1.7 billion. And worldwide, investments in quantum technology startups reached their highest levels in 2022 at just over $2 billion. Quantum computing appears to get the most attention, but research from McKinsey believes that we could see various types of quantum sensors and quantum networks hit the market first, as seen with the quantum key distribution network in Chattanooga. But quantum computers hold incredible power in developing Quantum 2.0 and making it a reality, and this is because of its ability to process the enormous amounts of data through AI. To learn more about the market opportunity, I spoke to leading technology analyst and 6'5" co-host Patrick Moorhead.
There's a ton of debate on when quantum computing will actually be able to do a meaningful workload better than a traditional computer. Okay. I believe we're within probably 3 years from that happening. Others say it's going to be about a decade. But what everybody agrees with is when we get this right, it is going to be breakthrough and enable things that we've never been able to do before, where we take operations that can be 10,000 times faster than being done on a traditional computer. And the only thing, I mean, it's a big deal, is first of all, you have to crank up the number of qubits, and then you have to improve the quality of those qubits before they essentially burn out and don't become usable anymore. And that really is the race. And then I view it working out very similar to how a GPU works, right? An NVIDIA or AMD GPU, which accelerates AI today. It's an accelerator, right? So your application will be running on a traditional computer, and through an API call, you will go out to the quantum computer just like you call out to a GPU to do these special functions. So I think we're closer than we'll be. And the great news is there's just a ton of players working in this space. And, I think companies like IBM, IonQ, Atom Computing, Quantinuum are really at the forefront of this type of technology. Swinging back to your Chattanooga question, because quantum computers essentially take an entire room and a facility, it's something that its lack of transportability is creating cities, right, that are leading in this. And by the way, countries, right? So most countries in Western Europe want their own quantum computer centers, and you see them popping up in the UK. France, we saw one with IonQ pop up in Switzerland, right? So just like we see in Chattanooga, there are power bases of cities. For instance, in Colorado, right, we have Quantinuum, Atom Computing, Cold Quantum, Quantum Corporation, multiple companies that are solidifying typically around universities or national labs. And that's where Chattanooga comes in, where they have national labs and colleges around Chattanooga that attract this to happen. So colleges, national labs, that's typically where you're going to see the power bases of quantum computing. And these colleges, right, it's typically physics, mathematics, or many of these have actual research in quantum computing that are funded by governments.
Mm-hmm. And so, diving in further there, it seems to be less of a race of companies competing against one another than nations. But I don't know if you have any background on the international race for this technology.
There is a quantum computing arms race out there for sure. And it's not just classic, the West versus China and friends of China, right? You now have each country doesn't want to be beholden to any side that they're on. Each country wants to have its own capabilities and not be beholden to maybe the United States, something like that. Japan is a real hotbed. Korea is a hotbed. And they all want to be putting research in, again, and it's about national security. But overall, most of the funding out of the U.S. is driven by the what is China doing, right? And China can't get there first, because if you think accelerating something 1,000 times, 10,000 times faster than even what a GPU can do, this type of power in the hands of nefarious players could be a real danger.
Now, just before Christmas, President Biden signed the Quantum Computing Cybersecurity Preparedness Act. The move more or less codifies his administration's effort to analyze the federal IT systems that soon could be vulnerable to quantum computers. It follows the U.S. CHIPS Act that dedicates $500 million over 5 years to build large-scale quantum network infrastructure around the country. The U.S. is also considering tougher export controls for quantum, but some experts fear that could stifle momentum, limiting a company's ability to become an international leader in this space. Plus, the U.S. faces a talent shortage in the STEM field, with research indicating that less than 50% of quantum computing jobs will be filled by 2025. This, as China has produced results that have nearly matched or exceeded the American approach. That's according to New York Times. Will public-private partnerships push the U.S. forward in the quantum race? Well, the city of Chattanooga hopes to find out. The network officially launched in late July. Follow along with me, Diana Blass, so you can stay connected with what happens next. Because the question is, who will win the quantum arms race?